We are now.
Oh shit, okay, cool, that's all good. Cool, so just for the camera, for whoever's missing, I'm Dr. T, Dr. Trenery. We'll find out who you are. Missing 11th person soon. So, could we go around and just like, when did you have Calc 1?
Last year.
Last year?
Last semester.
Beautiful.
Last year.
Last year?
Last semester.
Smith, that's good.
Last semester.
Say 2 years ago.
That's cool. Do you feel, how do you feel about math in general? Is that like something you like?
I like math, calc. Like have like a love-hate relationship with it.
He's crazy with calc. Don't want to lie to you. I've seen.
I'm sure. Yeah. Okay. All right. Thank you, sir.
Last semester.
Last semester.
Yeah, last semester.
This is beautiful. Beautiful. And was it at Regis, or would you have any transfers?
Here. Transfer.
Okay. Cool. Great. Thank you. So we are going to actually start today with a review of integration, which if you took it here, you probably just like stepped over the threshold of integration. You're going to understand integrals so well by the end of this class. Yeah, so get your notes out. We'll be doing some stuff. And again, I'm recording every class, and you'll be able to find it on my YouTube page. Highly recommend you subscribe to my page, not to get my numbers up. It's not monetized. It's just so that when I put it up, you know Calc 2 video's up if you need it. Let's talk about the basics really quick. So in world class, I'm scared to write on this because she said it was kind of screwed up. In world class, all sorts of good stuff is there. You have an assignment that's due Wednesday already. What a chump, what a jerk. I can't believe it, right? Like, how could I do that to you? It's easy. So, in world class, go to the content area. Some days I will want you to bring your laptop to class. We'll do work, actually, on our online homework system. But in the content area, you'll find the syllabus. So let me give you a rough breakdown. We're gonna have 3 exams. We're gonna have 2 in the middle of the semester and then a final exam. Those are 15% each. You can find all these deets in the syllabus if you don't remember what I'm saying. We will also, so we'll have exams. That's 45% of your grade at the end, 3 exams. We will have written homework or quizzes. And that's 15%, so that's 60%, and then web work, which is homework, this is how we'll do our homework, is, what is that, 40% of your grade, so it's huge. Who has used web work? Fantastic. Oh, beautiful, beautiful. So your assignment for Wednesday, and I'm going to check this before I come in, and then if you haven't done it, I'll get passive aggressive and congratulate everyone who has done it, because that's the way I roll. What I need you to do, this is homework, I think I called it homework -1, because I had already called something else 0. So this is the most primal homework. When I have to beg people to do this, it's always a red flag. It always worries me. So what I need you to do is log into web work and maybe change your password. Everybody could figure it out. They're all pretty self-defined. You will find instructions in the content area of web work on how to do this. So what I want you to do is just try. And tomorrow, if you're having any trouble, email me. I'm ttrenery at regis.edu. regis.edu. And let me know if you're having trouble logging in. Please do that. That's really all. And then I want you to go to one of the problems and try it. Guess it wrong. If you want to have fun, just guess it wrong. The good news is infinite attempts. There's lots of stuff going on there, Kevin. You still like, are you like, you don't have to be actively like tracking me, just so you know. I appreciate it. Okay, cool. Just so you, I don't want you to feel like you have to be the camera person. So get in here and try anything. Just put an answer in. Don't even read the question if you don't want. That's kind of fun. It won't matter. And that's homework -1. Log in, answer something, wrong or right. Homework 0. This is where things are going to get fun. This is a review assignment of integration. And today I'm going to do a review. I'm going to refresh your memory on what you need to know to get that assignment knocked out. And then I guess in the syllabus there's all sorts of other things. My office hours are Monday, Wednesday, right before this class, like 3 hours before we start. So 11 to 2, Monday, Wednesday. I'm in the math physics suite in the back end. And then on Friday, right before our class. So know that we do, it's okay to be tired. I'm exhausted. It's totally cool. I'm just jacked up because I'm on the stage here. Yes, sir.
So the homework, it says homework 0, not homework -1.
Oh, yes, homework -1 is almost done. You just need to get into, so for homework -1, go to homework 0 and just type a wrong answer into anything. You're pretty much almost there. Does that make sense? Does that help clarify what I'm saying? This one has to come before this one. So let's see, where was I? Oh, yes, questions.
It's not letting me log into that work for some reason.
When you say that, it's like it's not accepting the password?
Yeah.
Can I see what you're doing? And maybe after class we'll take a few minutes. Okay, would you shoot me an email? Just to make sure, we'll try to fix it after class, but just shoot me an email and say can't log in,
Okay.
and I'll check the creds that I entered. I could have misspelled something, it happens.
Alright.
Yeah, so I mean honestly, everybody seems to kind of be doing that. It's okay if you don't want to right now, it's no big
I
deal.
agree with you not to, that's fine.
It's okay, it's all good, yeah, no worries. In general, you probably won't need them. We'll have days where all we do is work on web work problems. We'll come in and it's just like a giant office hour. I'll be here to support you and you can support each other. But in general, you won't need your laptop. So is there any other bureaucratic questions or anything? I'd ask that you don't start on the homework though. So one of the things I'm really into is mindfulness and being present. It's like a big part of my life. I'm working with, I have a teacher of my own, I'm a Zen teacher, and I've been practicing Zen for like 40 years. And so like it's a big part of my life, and so I like to bring it in, and we won't always do this, but we will sometimes do this. And let's do it now since it's our first day together. I ask you to just stop doing anything for a second. This is great. This is going to be the easiest thing you ever did. Let's just take a minute. And maybe just close your eyes for a second. You've had your eyes open all day. You've been busting ass. Really exhausting. And just listen. Hear some sounds that are nearby. I hear sounds from our friends in the room. I hear that fan. What else do you hear? Do you hear anything far away outside this room? Just bring your attention to your breathing. It really doesn't matter how, but I would like you to notice where you notice your breath. So is it in the belly, is it in the chest, the throat, the nose, or the mouth? There's no wrong answer. just let your breath happen on its own. Stepping back. All right, beautiful. Thank you, friends. That's it. So, any questions before we get rolling? It's a dangerous thing to do a meditation this time in the afternoon, but we'll try to keep them short. I know you've had food, about ready to black out from the day already. Oh yeah, that's pretty bad. So let me just give you a quick overview, and maybe it's something you've never heard before. Calc 1, what do you cover in Calc 1? Somebody help me out here.
Limits, functions.
Limits, and functions, yeah. And then what's the big thing you cover at the end?
Functional theorem.
Oh boy, that's great. That's awesome. That's too fancy. What's what you cover it for about a month? What, differentiation, derivatives, right? So you do derivatives. That's what Calc 1 is about. So it's limits, but to understand the derivative, you need to understand limits. All right, let's try to shake some things up here. So if I have this function, f of x, and I want its derivative at a point x, can anyone remember that definition? No pressure, because you don't need to. Let me start, I'll start writing some stuff.
And the definition of derivative.
Yeah, the definition of derivative. Into, let's do a little hangman thing here or something. So you can help me out. Yes.
F of x plus h
Ooh, oh, beautiful. Yeah.
minus f of x.
Oh, so good.
H minus, no, h minus x.
Oh, just all good old H.
H,
Yeah, that's great. That is so beautiful. Does that look familiar?
Yeah.
Does that wake some ancient brain cells? It's kind of kicking them. They might feel dead, but you're kicking on them. So let's really quickly talk about what does that mean. I've got this function, y equals f of x, y, x-axis, and I've got this point x. This graph, does this make sense? You see this, and you understand what that means. That's good, because we gotta have some basics that we all share in common. So this is the point x where I'm taking the derivative, and then I've got this point x plus h. Now here I'm going to assume that h is a positive number, and it's generally a really tiny little number. When we write this, what we mean is h is really close to 0. And we can get it as close to 0 as we want. From the right, here's 0. So we could come in this way, or we could come in this way from the negative side. This is talking about both ways. Coming in from the left and coming in from the right. What is this quantity reduced to? And that quantity represents this. So let's see here. Here's f of x, that height. Here's f of x plus h. And so the top of this quotient is the distance between these two right here. So this is f of x plus h minus f of x. Just the height change. Wow, the height change. Does that make sense? Sound good? So I take the change in the height divided by the change in the horizontal, which is just h. So we can sometimes write this as change in f over the change in the x coordinate. And that's actually where the ddx notation comes from, because that delta means change. If you're a chemist, any chemists in here? Chemists, so you're all over delta, right? Yeah, you guys are all over. What about this one? What is that? That's basically the heart of the universe, right? Entropy is not negative. Isn't that what? Yeah. Okay. Yeah. This anyway, just having fun. Okay. So it's the heart of time anyway. So I've got this distance here on top, the change in f over the change in the input. And I'm hoping that as this gets smaller and these get closer, as this rides along that curve down to here, so maybe h is right, x plus h is right there. As I let that width get smaller and I look at this quotient, I hope it approaches some value. What I want to point out, now I'm not going to get into the details because I'm not going to teach Calc 1 again, but what I want you to notice is that Calc 1 is all about this. This is a difference and a quotient. Oh wow, if I could spell difference. Difference and a quotient. The derivative is a difference and a quotient. It's a change and a relative change. An absolute change and a relative change. This class is about the exact opposite. All semester. This class is about the integral. And the integral is about sums and products. It's literally the exact flip side of Calc 1. And let's talk about why and how. So let's, oh my God, this is not good. Maybe I hope we get moved to a new room. Do we have any spray? Like hand sanitizer? Oh my God, I don't think I should spit on it or anything. That'll be bad and kind of gross for our first day together. I'll spit on things later in the semester. What's this? Oh, wipes. Beautiful. Thank you. Man, you are just like providing. Thanks. And they're wet. Imagine. All right, we'll see what happens. Oh, look at that. Hell yeah. So let's talk about this integral, or the process known as integration. Leave that up for the second, for the time being. Okay, so a review of integration. Let's start off with a problem that we can solve together. So problem. Find this area. So I'm going to draw out y equals x squared, a parabola, yield parabola. I'm going to do that from 0 to 1. And of course then this is 1 squared, so the height is 1. And the area I'm interested in is the one between that curve and the x-axis. So we'll call that A right there. Find that area. Without using calculus, what would you do? So this is some ideas, and no wrong answers. Without falling back on this, if you remember it, what would you do out in the wild? Calc-free. Any ideas? $1 million prize has been offered. We just have to find that area.
Is it x?
So x is just a variable. This is going to be like, yeah, this is going to be a number here. What's it less than? What's this area? What's an upper bound on that area? Lots of them. Somebody give me an easy one. What's it definitely less than? What other area that we could easily compute? Yeah, nice. If I look at this rectangle here, this rectangle formed with a width of 1 and a height of 1, that area is 1 unit squared. So I know it's less than 1 for sure. It's clearly strictly less. Can we get a better estimate? That's good. That's a great first estimate. Can anybody cut this estimate in half? Simple geometry, that's all we're thinking. Don't get too fancy.
1.5?
How'd you come up with that?
I just like compute like the surface of the triangle.
Yes, triangles, exactly, yes. So I could also go, oh, it's less than the area of that triangle, right? Does that seem clear to everyone, that it's less than this area right here with a triangle, right triangle, with a width of 1 and a height of 1, because the curve sits inside there, right? So this little area is less than that, and the area of this triangle is 1/2 base times height, so it's 1/2 unit squared. Cool. What's it greater than? Give me a lower bound. I'm going to take the easy ones. It's definitely greater than -2 because areas aren't negative. So what's the lower bound I could have here, do you think? 0. Yeah. So let's just go low-hanging fruit, right? Super low-hanging fruit. So we can say this, and then it starts to get a little tricky because we've used up all our favorite shapes, rectangles and triangles. So what we could do is take another approach. Never going to learn, apparently, here. So here's an approach used by the Babylonians. The Babylonian people, one of the first societies, first civilizations ever, was doing calculus. The Babylonians, this was literally discovered like maybe less than a decade ago. The Babylonians, we always think, oh, the ancient peoples, like we're so much smarter than them. Oh, look at us, we drive in cars. I've got a cell phone, my God. The ancient peoples were beyond our comprehension, smart and clever. The Babylonians used calculus to figure out the position of Jupiter in the sky at any time. They actually used integration for this. This is a recent discovery. So the stuff we're about to do today, Babylonians doing it, thousands of years ago. Not with the same symbols, but the ideas were all there. So let's take their approach. And their approach was this. We're just going to approximate this with smaller things that we understand. And the one thing humans understand more than anything is the freaking rectangle. The rectangle is like synonymous with humanity. Do you happen to see any rectangles in this room? Yeah. It's freaking the table. The room is a 3D rectangle. The building. Colorado? Everything is a freaking rectangle for us. So I'm not a big fan of rectangles. I think they cause problems for us emotionally and stuff like that. But what we're going to do is approximate this thing with rectangles. So one way I could do this is say, okay, well, here's halfway mark. How high is this rectangle? What is the height of that rectangle? Somebody else who I haven't talked to, I'll start calling on folks as soon as I learn their names. Jose. Where's Jose? Jose. Sorry, I got this damn thing backwards. Sorry. Hi, Jose.
Yeah.
How high is that rectangle, sir?
I'd say 30.
How'd you come up with that? So remember that we have this relationship. So if the x-coordinate is 1, the y-coordinate is 1 squared. So what is the height associated with half then? What's the y-coordinate? If x equals a half, what's my y?
Oh, 4th.
There you go. Perfect. Beautiful. You were thinking, not deep. That's all good. Yeah. Cool. Awesome. So the height of that rectangle is 1/4. Does everybody see that? Because it's a half squared. Does this all sound good? Oh, so we're not just reviewing calculus. We're warming up our math in general. You probably don't have any other math classes this semester unless somebody's taking linear algebra. Anybody doing that?
Discrete math.
What's the discrete math?
Yeah.
Oh, well, who's teaching that?
Jim.
Oh, cyber?
Yeah.
Oh, okay, cool. That'll be a good course. That'll be good. Very computer science oriented. Very computer science. So we got a fourth. So now, look, I've got this rectangle, and then I've got another rectangle. So I've got this 1/2 base rectangle, height 1/4, and then I'm going to use the same system. Notice how the height of my rectangle, I'm using the right end point. Here's an interval, here's an interval. I look at the right end point, go to the curve, and get the height of my rectangle. So this one here, this was 1/4. This one is exactly 1 unit high because it's 1 squared. So we've got this thing that kind of looks like this right now. We've got this approximation. Here's this little rectangle, and then this bigger rectangle. And so let's see, what is our area approximation? Here, this is 1/2. This is 1/2. And when I say that, I mean the width. This is 1/4 high. This is 1 unit high. How do you find the area of a rectangle? Height times base, base times height. One side times the other. Does this sound good? Area of a rectangle, let's just get that up here. If I've got B units that way, H units that way, then the area is base times height. Super essential to know that. So this area right here is base 1/2 times height 1/4, so that's 1/8. This area is 1/2 times, why did I write that? I meant 1, excuse me. Height of that is 1, sorry, I hear erasing happening already. The area is 1/2 units squared. So the approximate area is the sum of those two. It's going to be 1/8 plus 1/2. Now let me write this in a way that kind of steps back just a little. This was 1/4 the height times the width of the rectangle, and this was 1 the height times the base of the rectangle. Looking at it this way is going to become an important skill for us. But in the actual computation, what do we got here? 5/8. When we add those two together, is that more or less than the true answer? How's that? How does this estimate of this area compare to the truth? 5/8 units squared. Well, it's already more than the thing we said. We know it's less than, right? You already said it's less than 1/2. We know that. So that's way too much. But look at it. This is the area we want. There's a lot of overspill there, right? So this is an overestimate. This is way over estimate. How can I improve that estimate with the same idea? Kevin, I am very worried about how much work you're having to do here. Are you okay?
Yeah, I'm
Okay.
paying attention.
Awesome. Okay, fantastic.
What's the question?
Oh, yeah, great. Yeah, too many things going on. I'm a little bit of a spaz, clearly. So, how could I improve that estimate? What do you think, Kellen?
More rectangles?
Love it. Beautiful answer. Have you had calc before? Yeah, of course you have, but you're thinking of the tinier rectangles, right? Beautiful. So, to improve this, we could have more rectangles. So let's take a look at that. We could actually do, let's get the same back. So this is y equals x squared. And then we've got 1 here. So let's do quarters. So there's 1/2. There's 3/4. There's 1/4. And let's make some rectangles. And what we're going to do is, notice I have 4 sub-intervals. I'm going to use the right endpoint of each sub-interval and go up to the curve to get the height. So here, I go up, I go across, I go up, I go across, up, and across, and I've got to stand, damn it, and across. Do me a favor, find the areas of those and get us an estimate. You can do it on paper, in your head, whatever you want. I can't do it in my head because it's little fractions and stuff. What is the total area of these 4 rectangles. So let's just take a second to do that. Let me find my T.
That's yours.
Yes, thank you. I was worried I left it in a bathroom. It's already creepy enough to have to take it into a bathroom. Yeah, and I see calculators out. That's beautiful. When exams come, generally I don't allow calculators, but you won't need them. I want you to become strong, powerful mathematically. Oh good, nobody's crying. One time I had somebody break into tears at that news. I'm glad we're all resilient enough to handle it. First thing I would do is make sure I get those heights. Remember, the height is just the x-coordinate squared. So that's 1/4 squared. Wow, really poorly written. 1/4 squared. This is 1/2 squared. This is 3/4 squared. This is 1 squared. Those are going to be my heights. The bases are all the same, 1/4. So I'm going to write this up. Approximate area equals sum of area of rectangles I'll write this up, and hopefully it looks like I'm going to have some folks with answers for me. I'm going to write this as sum of base times height. And then I'm going to write out what that looks like. So that is going to be 1/4 times 1/4 squared plus 1/4 for this base. Remember, these are all a quarter. They're all identical. They don't have to be, but it sure makes life easier. 1/4 times 1/2 squared, 1/4 times 3/4 squared, and then 1/4 times 1 squared. Anybody got a number off that? Alexander's. Do you have?
I don't have a number.
You don't have a number, okay. That's all right.
Yeah, I didn't do it.
That's okay. Cool. Anybody got a number for me? Decimal or fraction?
It's 7/16.
7/16. Oh, that's very nice. Let's take a look at this. 7/16. That sounds hella right. It's definitely less than a half, right? It's just like barely. So we know that it's not ridiculous like this one was. So it's got that essence of rightness to it. If you're having trouble with the fractions, just tell me in private or something. I don't want to make eye contact about it right now. People aren't good with fractions anymore. It's a lost art. All right, so Kellen gave us a great idea for how to get a better estimate. This is still over the truth, right? Because the area of those rectangles is clearly more than the area of this thing underneath them. Somebody help me out here on Vincent. Hi, Vincent. How could I make a better estimate? Hell yeah, that's always the answer in this class. More rectangles, good stuff. So we could do more rectangles. Now this is going to become painful, and we're not going to watch me divide this up into 8 parts and do it, but we could actually imagine what that would look like, right? So a better estimate, I'm going to first just write up that summary. Better estimate comes from, now watch this, I'm going to introduce a few terms here. A finer partition. Now what do I mean by partition? That means the cuts that I make. Smaller cuts or more cuts. So this is smaller horizontal faces for the rectangles or more rectangles, and one gets you the other. If you want more rectangles, they've got to be smaller. If they're smaller, they'll be more. It's a really lovely symmetry there. So, let's not go to the 8. Let's just do this in general. One last time. All right, draw this freaking picture again. Here's good old y equals x squared, x, y. All right, now I'm gonna get crazy. Now some math is about to happen. This is like arithmetic so far, right? So now we're gonna math this thing up. I am going to cut this thing into an unknown number of pieces. So I'm gonna make a cut that looks like a definite width, but it's just representing an arbitrary cut. I'm gonna put a little dot, dot, dot there, and then I'm gonna finish it up at the end. Then what I'm gonna do is go through here and call this x1, x2, x3, x4, dot, dot, dot. This very last one I'm going to call x sub n. I don't know. N equals the number of cuts. Here n was 2. Here n was 4. I would like to do this for any number n. 3, 1,000, whatever. I want to think about this problem in the most arbitrary sense. So this is totally arbitrary. Let me stop for a second. It's a lot. I'm giving you a lot. How's this feeling? We follow me. Yeah? Yeah? Cool. Make your shoulder hurt. As long as you're not having like heart trouble, you grab it. That's for me to have. I'm the old one. So, number of cuts is n. So let's think about this process. Let's draw little rectangles using the right side. So I go up from the cut, the right side of the cut, find the height, and then go across. And then here I don't quite know what's happening, so I gotta come back here. Do that. So, and there's other stuff happening in the middle there. Does that look okay? Yeah. And then I'm gonna figure out the height of each one of them. Now, let's say they're all the same width. So let's suppose each cut is this wide. So that's a delta change in x, y. So that means the base of each one of these is delta x. All the same. Okay, cool. And so now I can find the height. The height of this first rectangle is the value of this curve at x1. So this one is x1 squared high. This one is x2 squared units high. This one is x3 units high. x4 squared high. This one is, how high is that last one? X sub n. And what would x sub n actually be? Because I kind of realized it was 1. Yeah. So the last one is actually just 1 squared, but we could have x sub n. And then this one is x sub, ooh, what's that? It should be there. What do you think, Amber? You already told me. I'm making you do double duty here.
Just x0 to x0 squared.
Yeah, so, oh, sorry, I wrote that 0. I actually meant a little blank to fill in. Sorry. But that's the right idea, yeah. If this is x sub n, this is x sub what? N minus 1. It's 1 less. So that's x sub n minus 1 right there. So this is x sub n minus 1 squared. And oh my gosh, we can add those up, but it's going to look weird. So let's do our sum of the areas. So the sum of the areas is going to equal the sum of the heights times the base I kind of want to put that base second. I just had these reversed right over there. So the first one is going to be, the height is x1 squared times the base delta x. Then the next one is x2 squared times the base delta x. And then this just keeps on rolling all the way till we get to the right side. Here I'm going to have x sub n minus 1 squared delta x. And then my final one, I'll just write him as x sub n, but we know is 1 squared. And that's just a symbolic version of everything we've done so far today. No clock, so I was looking for a clock. Let me stop for a second. Take a look at that. If you saw that, could you make some sense of it? And if not, what would help you make sense of it? What's confusing there? Please ask. We're going to be good friends by the end of the class. And maybe you don't even know what to ask yet. Yeah. And that's a fair thing too. Let's make this look a little prettier. So the next thing I'm going to do is I'm going to use some notation. I'm going to use summation notation. So use summation notation to make this compact. This expression, so when I say this, I mean this thing here, to make this star compact. So let me write that up here and then let's see how we feel about it. First I put a big capital sigma. That is capital sigma, stands for sum, essentially in math. Lowercase sigma, if you ever do, anybody had stats, statistics, done any of that? No? Little lowercase sigma stands for variance, if you ever take that, but we use this guy right here. And so, look at what's changing between term to term. It's this little number down here. Everything else looks the same. The squared is the same. The delta x is the same. The only thing that's changing is the index, the subscript on the x. That's the only thing that changes from term to term. So watch this. I'm going to write x sub I squared times delta x. Now when I equals 1, it looks like this. When I equals 2, it looks like this. When I equals n, it looks like this, and everywhere else along the way. When I equals 7, it looks like this. X sub 7 squared delta x. The seventh rectangle has this area. So when we come up here, we want our I to run from 1 to n. There are n different things in this sum. So what this means is, when you see this notation, really important that you do understand this, this means we're going to let I take on all values, all whole values, from 1 to n, and add the results. So this is going to be essentially, when I is 1, it looks like this. When I is 2, and I put a plus there because I'm summing. When I is 3, and then all the way down to our last one. But this notation here is the key. Does that look familiar-esque? That's all we need right now, familiar. Seen this before in my lifetime. Good. We have this idea that the more rectangles, the more accurate we are. What if we could have infinitely many rectangles? That would be the best, and that would be perfect if we had infinitely many rectangles. So what we do is we say, okay, we're going to compute this sum. Oh, we're almost done. And honestly, today's one of the toughest days because you're coming in after not doing this for a while. A lot of math on the board. But to get the precise area. We let the number of rectangles go to infinity. We'll go to infinity. And think about what happens. The more rectangles you have, the tinier the bases go. So you could think also the bases are going to 0 as well. If I had 1,000 rectangles in here, you could probably not even see the bases. They would be so tiny. So we could say that the number of rectangles go to infinity, or let that delta x go to 0. That's also a way to get there. And the way we write that is this. Limit as n, which is the number of cuts, the number of rectangles, goes to infinity. Sum I equals 1 to n, x of I squared delta x. And this, my friends, is what we just paid a lot for. It's called a Riemann sum. This part is called a Riemann sum right here. Taking the limit moves us into the calculus realm. Anytime you take limits, calc is involved. So the shorthand for this crazy ass process is this: integral. And where did we start? We started at x equals 0 to x equals 1. The function we are finding the area of is x squared. So look at how this goes. The limit, this part here, becomes this symbol here. And this thing that's changing becomes this part, that's called the integrand. And then the delta x just becomes dx. And now we've got something that looks like hopefully what you saw toward the end of Calc 1. Let me write it up here. And we've got that the true area is equal to integral from 0 to 1 x squared dx. That represents the true area. But what it represents, and what I want you to think in this whole class, every time you see an integral, that is this crazy process. So this symbol here, this isn't a thing, this is a process. It represents cutting up into pieces, finding rectangles, letting the number of rectangles go to infinity, and adding up the areas all the way along. Calculus is a process. This is one of the great ones. So, how do we do that? Now I've got it turned into something that you hopefully saw toward the end of Calc. Let me find it. Let me let you think about that. How do you do that? If somebody knows how to do it and would like to explain it to us, that would be beautiful. If I just gave you that problem today and said, take a minute, give me the answer, what would you do? Anyone feeling confident enough to step out and...
I have an idea.
Oh, I love it.
Are we gonna use like derivatives?
The anti-derivatives? Yes.
Exactly.
Yes. Because yes, we are. And yes, yes.
I think I solved it. I don't know.
Tell me what you did.
I
That's right.
took the antiderivative. You said it is right. I took the antiderivative of x squared, which is like x cubed over 3.
Yeah. So you added 1 to the
And
exponent.
then divided by x.
And divide, I like to write it as 1/3, same
Yes,
difference,
yes,
same
thing.
difference. So take the antiderivative of the integrand, beautiful.
And then I plugged 0 in for x, and then added it to the same thing, but added 1 in for x. Yeah,
Love
I did that.
That's
that,
freaking
that
awesome.
one too.
That's beautiful. That warms my heart. Thank you, gentlemen. Thank you. So look, I wrote it a little different here. So let's take a look. The first thing that Alexander used here to find the antiderivative of x squared was what's called the power rule. So the power rule for integrals, let's write it out, says this: if I have the integral, now there's no numbers here. This is a definite integral. It represents a number. This is the indefinite integral. There's no numbers. It just means take antiderivative. So indefinite integral just means find the antiderivative. That's all it means. It's part of that, but it's not the whole thing because we still have the 0 and 1. So step 1 is use the power rule. If I have x to some exponent, add 1 to the exponent, divide by the new exponent. So here the exponent is n, so this is x to the n plus 1, and then I like to put 1 over n plus 1 in front. And then what's the thing we generally tack on?
Plus C.
Thank you, plus c. Plus an arbitrary constant. Because I want it so that when I take the derivative of this, it gives me this. But there's lots of constants you can add here. When you take the derivative of this side, this goes away. And you're just left with x to the n. So we've got that. We don't generally write the plus c over here. So what you can see that what Alexander did was take 2, bump it up by 1, and divide by the new exponent. This notation means evaluate at. So I'm going to take this thing and I'm going to evaluate at x equals 1 and x equals 0 and find the difference, subtract. So what that looks like here is you put in the top one, so it's 1/3 times 1 cubed, minus, plug in 0, 1/3 times 0 cubed, and our final answer is 1/3 unit squared. So that's the true area, 1/3. That little parabola is exactly 1/3 of this whole thing here, of that square. It's just 1 by 1. It's just 1/3 in terms of area. That's kind of cool. So this is what you're going to need to do, but this process of thinking like this is something we're going to practice over and over again. Question?
No.
Oh, okay, cool. Awesome. That's all right. No sorries needed. No sorries needed. What time are we at? I don't have...
301.
3:01. Awesome. We got a few more minutes here. So let me point out a few... Actually, let me sum this up really quick, and then point out a few things to you, and we'll kind of call it a slightly early day. And then I can help folks get logged in, and web work and stuff like that. But let me write up, who was it that said the fundamental theorem of calculus earlier? It was Alexander. Yeah. So this thing that I just used was called the fundamental theorem of calculus. Part 1 or 2, there's 2 parts to it. And it's kind of cool. Let's write it and then think about the incredible power behind it. It says that if someone asks me to find the definite integral from a to b of some function f of x. Now you can always interpret this as area, and it's very useful too. So let's say I've got some weird ass function y equals f of x. And here's a on the x-axis, and here's b on the x-axis. We can think of this as the area between the curve and the x-axis. So that's always an interpretation that's available. It gives you a lot of power. You can see things that might not be obvious mathematically, but geometrically they are. So fundamental theorem of calculus, part 1, we'll just call it part 1 since it's the first part we're doing, says to find this. Now remember, this is a process. This is a crazy freaking process where you cut this up into infinitely many rectangles and add up their areas. That's what this means. Fundamental theorem of calculus says, just forget about the rectangles, okay? That's kind of a lie. Instead, find the antiderivative of this integrand and evaluate it at a and b and subtract. So let me write up what this means. F of x, big F, is an antiderivative of little f. So where big F equals an antiderivative of little f. And what that means is that the derivative of this is little f. A lot of stuff going on. And then this, remember what this means. This means to plug in this top number, plug in the bottom number, and subtract. It turns that crazy infinite process into a subtraction. That's it. That's the fundamental theorem of calculus. So, what we're going to practice for the next roughly 2 weeks is remembering how to do this. And then we're going to push it forward, and you're going to learn to do more techniques, different ways of getting this done. And you're going to be incredibly powerful by the time this all comes out. So now, in world class, I'm going to end our talk in there today, just so you come back. I hope you do. In world class, in the content area, I have put for you the greatest calculus integral derivative table ever created by humankind, I believe. It might be the single greatest math reference ever created. It was in the book I took calculus out of. And it's just got everything in it. You can use it, just check it out. It's a treasure trove of mathy fun facts. But you've got an integral table to use there. And that's something you definitely can have at the first exam. So you might want to check it out. If you have one you already love, use that. It's cool. Math hasn't changed in a long freaking time. That's good news. All right, my friends. Well, thank you for being here. This is going to be fun. Yes.
What's your YouTube channel?
Oh, yeah. So go to if you go to World Class in I think it's in the content area. I have a link to it. If you just go to YouTube and search on Dr. T Trenery, yeah, give it a shot. Let's see if that works.
It's linked in your.
It's linked in there.
Yeah,
Awesome.
Just under
Cool.
Dr. T's YouTube channel.
Beautiful. Beautiful, beautiful. All right. Nice meeting you all. Thank you. See you on Wednesday, right?